Ladies and gentlemen, two things before we get started. First, I'm compelled to tell you that you are being recorded right now. Right? So anything stupid that you say may end up on this recording for everyone else to hear. Okay? Second, when I record, that's the microphone up on the front. So I walk around a lot, and so if it seems like I'm yelling, I kind of am because I want to make sure the microphone hears me. So I generally talk louder. Yes, Ames?
So the microphone is for you could listen to what you said.
Yep. You'll hear the whole thing. So
tomorrow you're gonna listen to everything we said today.
yep. Exact replica. Actually, I'll post it probably like during my lunch. I usually post it on YouTube, so you can go and watch it. And if that's really what you want to do, you know.
Oh, okay.
Maybe if you're having.
What's your YouTube account?
I'll share it with you. Actually, I will put a link on the calendar, so it'll say class recordings. If you just go to the calendar, click it, it'll take you right there. So if you're having trouble sleeping tonight, then you can just pop this bad boy on. And sweet dreams, everybody. So, all right.
That's how like random noises.
Let's not do that. Let's not make random noises. All right. On Friday, we talked about the idea of conservation. And we said that when things are conserved, regardless of what it is that we're talking about, that means that the amount of that quantity or material or whatever it is we're discussing remains constant. That if we looked at its amount at the beginning of a situation and the end of a situation, it would be the same. One of those things that is conserved out there in nature is energy. And so the total amount of energy in a closed system will remain constant. So there are some conditions that we have to meet in order for us to see this idea of conservation of energy. First, we got to be talking about a closed system. That means that nothing interacts, right? We can't be putting more stuff into it, or we can't be heating it up or something like that. That changes the amount of energy, okay? Second, when we talk about the total amount of energy, we're talking about the total amount of energy. And that takes into account all kinds of energy like, the three that we're concerned with, kinetic and gravitational potential and elastic potential, but then also things like chemical and heat and nuclear and all of those things, which, let's face it, big picture-wise for us, really aren't that important to our everyday sort of lives, at least not how we see it. Okay? So, we want to talk more about the idea of mechanical energy, these everyday things that we deal with. And I said I wouldn't make you write it down a third time, so I got it for you there on your outline, right? But mechanical energy consisting of the sum of those three, right? Kinetic energy plus gravitational potential energy plus elastic potential energy. Okay? And I think right towards the end of class, we got to this idea of that under the right conditions, we will see not just a conservation of total energy, but more specifically, a conservation of mechanical energy. When there are only conservative forces acting on the object, mechanical energy is conserved. And so I think the next thing we talked about was what was a conservative force. Is that right? Is that kind of where we left off on Friday? Yeah. So, conservative forces. First, conservative forces do not change the total amount of mechanical energy in a system. And we talked about that there were two examples of conservative forces. Gravity is a conservative force. And then things that are elasticy, like trampolines and rubber bands and bungee cords and things like that, are also conservative forces. And we said that what makes them conservative forces is that when they act on an object, when they do work on an object, the total amount of energy or mechanical energy doesn't change, but we will see a conversion from one form to another form. And I think the example that we did in class was this idea of the ball and dropping it to the ground and then letting it roll to a stop, right? We did that, right? Okay. So we dropped it, right? And then it rolled, blah, 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 and then it stopped. Okay? So we talked about that there were really two parts to that motion. The first part, when the ball was falling, and the second part, when it was rolling along the ground and coming to a stop. So first, when it's falling, right? What's the force that's making it fall? Gravity, right? And then Jillian, there's a force acting on the ball. Does it move because of that force? Yeah. So does it fit our definition of work that we introduced earlier in this unit? Yeah, it does. But we talked about the idea that if we start examining the energy, or the individual types of energy, right, as it falls, what happens to its kinetic energy? Okay, Rhea? It increases, because what happens to the ball as it falls? What happens to the ball that makes the kinetic energy go? It gains more speed, right? It goes faster and faster and faster, right? So its kinetic energy increases. But at the expense of what, Rhea? The potential gravitational, right? That kinetic energy goes up as potential gravitational goes down, right? So this work that the gravity does is a special kind of work where it doesn't change the total amount of energy, it just converts one form into another. Okay? When that's the case, when there are only conservative forces acting on an object, mechanical energy is conserved. I think you guys already wrote this down. Okay? Maybe not, but. More importantly, though, we want to mathematically represent that idea. And I wrote these down for you because these get a little confusing. Okay? That when mechanical energy is conserved, MEI equals MEF, where the mechanical energy initial equals the mechanical energy final. And isn't that the gist of conservation? Right? It's the same at the beginning as it is at the end. Now, that's true, but earlier in this unit, we talked about that mechanical energy is made up of three things, right? Okay? Kinetic, gravitational potential, elastic potential. So we can actually expand this formula out to look like this. If we look at the kinetic energy at the beginning of the situation and the gravitational potential energy at the beginning of a situation and the elastic potential energy at the beginning of a situation, and we add all three of those together, remember, it's a sum. So if we take each of those three individually and add them together, and then we look at the three of them individually at the end of a situation and add those together, we would find that the total remains the same. Good there?
Yes.
Okay. Let's take a look at a specific example of this so we can start looking at the numbers. So, yes, Andrew, go ahead.
So already write down the mechanical energy is consumed.
I think we wrote that down already, didn't, like, up above the top, or at the beginning when it says, when only conservative forces are acting on the object, mechanical energy does not change.
Acting on an object, mechanical energy is conserved, meaning that meaning that it stays the same.
Gotcha. That's what conservative forces do, okay? That mechanical energy is conserved. Yes, more.
What are like the I's and the F's?
Okay, I stands for initial, F stands for final. So we talked about the idea more at the beginning, that if we look at something that is conserved, that means that if we measure it at the beginning of a situation and at the end of a situation, it should be the same. Does that make sense? So mathematically, we represent that with I and F, where if we look at the energy initial and the energy final, they should be equal. Does that make sense? So let's do this example, and I think it'll make a little more sense, okay? All right. You guys have this whole situation laid out for you along the left-hand edge of your outline, but I have mine broken up into individual pieces. So, a dire situation has arisen. There is a building on fire. So this woman grabs her purse, right, because you can't go anywhere without your purse, okay, even if the building's on fire. And she stands on the ledge of a window, because the flames are closing in on her. Look, you can already see them shooting out of the building, right? So she decides that this is her best option. She has to jump. So she stands on the ledge of the window, ready to jump. Does she have energy at that point in time? Sure, right? What kind of energy specifically? Gravitational potential, okay? She's not moving because she's just standing there on the ledge of the window, so no kinetic, right? But because of where she's located relative to the ground, she has gravitational potential energy. How much? 10,000 joules. Now, we don't know her individual mass, and we don't know how high she is, but some combination of her mass, 9.8, the effect of gravity, and her height off the ground gives her 10,000 joules of potential energy. Good there? Okay. So Maura, going back to what we just talked about, right? In this situation, that would be our initial situation, right? Our initial condition is kind of how we refer to it. So is there any kinetic energy at that point in time? So KEI would equal what? 0. We already talked about that there is some gravitational potential energy, 10,000, right? Is there any elastic potential energy? Is anything being stretched or compressed? No. So if we look at those three individually, right, and add them together, what do we end up with as the total? 10,000. Does that make sense? Okay. So that's the I. Okay. All right. So she jumps. What starts happening to her as she jumps? Andrew.
She falls.
She falls, and as she falls, what starts happening to her?
She's screaming.
Yes. What starts happening to her motion?
Oh, it's being absorbed.
Let's go. What starts happening to things as they fall? They go what?
Faster.
Faster, right? So that's going to cause an increase in what kind of energy? Kinetic, right? But as she falls faster, what is also happening?
The potential is going down.
Because she's getting closer to what, Andrew?
The ground.
Right. At one point of her fall, this is not the second picture on your guys' picture, this is actually the third picture on your guys', okay? Right? At some point in her fall, she has reached a point where her potential energy has gone down by 5,000. But what have we seen about how much her kinetic energy has increased? 5,000, right? So now if we look at the sum of these, what do we end up with? What's the sum of 5,000 and 5,000? 10,000, right? Where did this happen? It's easier to see on your guys' picture than it is, individually like this. Where does this happen? Noor. In the middle of her fall, right? Because Noor, in the middle of her fall, how high is she compared to the beginning? Not as high. How much not as high specifically? Well, she's half as high, right? So if she's half as high, how much potential energy does she have? Half as much, right? If she's got half as much potential energy, she's got to have that same amount of kinetic energy to get us back to the total. But that's not the end, right? As she continues to fall, what continues to happen to her? Christine, go ahead. Because as she continues to fall, she continues to get closer to the ground, so that makes her potential energy go down. But as she's getting closer to the ground, what happens to her speed? She goes faster, right? Until eventually she reaches a point, right, where she gets to the quote-unquote ground, okay, which won't necessarily be the ground in this case. But here, these brave firefighters have this trampoline waiting for her, and we're good to go. Okay? So 2 things about this picture. Okay? Actually, 3 things about this picture. 2 unrelated to the topic of conservation of energy. 1 related to the topic of conservation of energy. So first, unrelated. Whenever I see this picture, it always reminds me of the best day in elementary gym class, which is the parachute, right? Yeah, parachute day in gym class, and You know what, Trey, you know what I'm talking about. Don't play it cool like that.
I don't know what you're talking
really
about.
Come on.
No, because like you think rainbow parachute.
Like,
Oh,
yeah, you
yeah.
know what I'm talking about. Yeah.
Sit
Yeah.
on it and like stays.
Right. Yeah.
Go on,
Everybody goes
everyone
everybody
goes
goes
under.
inside. And, yeah. Yeah. You know what I'm talking about. Right? Best day of elementary gym class. Right? Then everybody stands on the side and like you shake it. You throw like the Nerf balls in the middle and they pop out like popcorn. And, yeah. Good times, everybody. Good times. Glad we got that on recording so we can all relive that memory. So, good. Second, unrelated topic. So you see this like, this big trampoline thing that firefighters have like in old movies and stuff like that. And I mean, nobody would jump out of a building into a trampoline now, you know what I'm saying? Like they would just get a big ladder and take the ladder up there. But I wonder if like they still have this big trampoline like in the attic of the fire station, and like every spring they go to clean it out and they're like, let's just throw this thing away. We never use this thing anymore. And somebody's like, no, what if the ladder's broken sometime and we have to like jump out of the building, so that's, yeah. Yes, Kathy?
Well, it's not really a trampoline.
No, it's not. It's more
It's a heavy piece of cloth.
Yeah, it is more like,
So you don't have to forget.
I know, but that's actually going to lead me to the next thing, Catherine, okay? So that leads us to the related topic, so.
It's just gonna like fall.
Yeah, so let's make it a trampoline, because that makes my transition a little better if it is a trampoline, so. Yes, Anthony?
Another unrelated type of thing is why is she smiling in the fool's picture?
I think she's yelling. I think that's more a cry of terror,
Yeah,
so.
yeah, she looks happy. She definitely looks scared there.
Yeah.
But in the fool's picture, she looks happy.
Yeah, I think that's more of a, I think it's more what?
It's like, yeah, well, she's happy that she saved her purse.
That's true.
I know, but
So-
she lost it like halfway down.
Yeah, see, now, actually, too, later on, when we talk a little bit about acceleration, we'll see that this picture is actually accurate, because even if she loses it, it still falls right next to her the whole time,
But
so.
like, how would they know that she was gonna land in that exact spot? Because the trampoline looks pretty small.
Yeah, I just, that's why we don't use this method anymore, you know what I'm saying?
I know, wait,
So-
how do they, like, what if they, like, rips out of their hands? Like, she hits them, there's like, oh, I can't hold on.
That's what I'm saying, there's definitely some flaws to this method, But, so Catherine, I understand your point, but let's say that it is a trampoline, okay? All right, so if it is a trampoline, okay, when she hits the trampoline, right, she's going very fast. So she has a lot of kinetic energy, but no gravitational potential energy. What does the trampoline do to her? Nora. Well, what does it do to her speed? Because what do we want her to do eventually? Stop, right? So it has to make her speed go which way, Nora? Down. So her kinetic energy has to decrease, right? But how does the trampoline make her kinetic energy decrease? What does it do?
Gives her elastic.
Well, it stretches out, right? Because as she lands on it, it stretches underneath wherever it started. So there is a decrease in her kinetic energy, but what would then have to happen?
This is semi-related.
Well, let's do this one related first, then we can do the semi-related, right? If there's a decrease in her kinetic energy, what would have to happen then?
Her potential energy increases.
Which kind of potential energy, Rachel?
Gravitational. Elastic.
Okay, so going back to this, right? Now on the other side of that, eventually her kinetic energy would end up being 0 again, right? But this total has to still stay 10,000. As long as either one of these increases to keep it 10,000, we'd still have conservation of energy. Does that make sense? Okay. Catherine, do you want to go with your unrelated thing right now?
Yeah, I mean, if it was a trampoline.
Yep.
And like they're holding it like maybe a bit higher than your waist.
Yes.
Wouldn't she like hit the ground?
Possibly, yes. Okay, that depends on how stretchy the material is that we're increasing the elastic potential energy, because that plays a role in how much it actually stretches. Something like, a rubber band can stretch a lot, right? but something like a trampoline, right? If we attach, Catherine, if we attached you to this rubber band, okay, and let's say it doesn't break, right? If we attached you to this rubber band, it would have to stretch pretty far in order to stop you. You know what I'm saying? But a trampoline only has to stretch like this far to stop you. Does that make sense? Like when you jump on a trampoline, it only really stretches out about this far when you land on it. You know what I'm saying?
Well, yeah, I mean, the one that they were holding
Right.
probably wouldn't have springs on it.
Right. You know, but I'm saying that how far it stretches is related to, for lack of a better term, how stretchy it is. It's something that we refer to as the spring constant of that material, okay? And different things can cause changes in elastic potential energy by different amounts based on how stretchy they are, okay? When you jump on your bed, okay, like when you're a kid, you jump on the bed, right? The bed only scrunches down like this much, like, a couple inches when you jump on it, because the springs that are inside of it are not as stretchy as this rubber band. You know what I'm saying? It still does the same thing, but how far it stretches would definitely depend on how, quote unquote, stretchy that material is. Does that make sense? So yeah, it would definitely, how much you want it to stretch depends on what it is, right? So let's transition this, okay? When you jump on a trampoline, is mechanical energy conserved?
Yes, because the energy is conserved all the way down.
Okay, that's true. Catherine, go ahead.
Because when you jump up, the energy is the same as when,
Is it?
well, when, like in a full jump, when you jump, when you're in the air,
Uh-huh.
it's the same, and then when you go down and come back up, it's the same.
Okay. That's true conceptually. Okay? But in actuality, is it true? Let's say you get on a big ledge, not a big ledge, but maybe you ever see Cirque du Soleil? You ever see Cirque du Soleil? Sometimes they do like trampoline acts and Cirque du Soleil stuff, okay? If we drop something on a trampoline, I take it here, I take whatever I'm dropping, a bowling ball or whatever, and I drop it, will it come back up to me where I dropped it from? It doesn't, right? Or if we do this, no, I don't have a bouncy ball in here, but if you take like a bouncy ball, right, like a super bouncy ball or whatever, right, and you drop it, does it ever come back up to the height you started it from? It doesn't. Okay? If mechanical energy really was conserved, would it? Yeah, because when you drop it, what kind of energy does it start with? Potential gravitational, right? And if you dropped it and it bounced and everything was conserved, how much gravitational potential should it end up with? The same. And if it had the same amount of potential energy, where should it end back up? Exactly as high as you dropped it from. But that doesn't happen, right? So, is gravity the only thing acting on that object as it falls through the air? No, right? What else does it have to contend with?
Wind resistance.
Wind resistance, air resistance, right? Or, in the case of like me dropping the ball on the floor itself, right? We said that there are only two kinds of conservative forces, gravity and spring forces. And that means that everything else is what we call a non-conservative force. So,
So what you said, so what's mechanical energy conserved?
let's do that tomorrow when we talk about let's finish this part up. And I kind of changed my plan as far as what order I wanted to go in right in the middle of this lesson. Okay? So we're going to go to the back and fill out the rest of like the outlining stuff.
Okay.
And then we'll do those questions tomorrow as like a review of these concepts. Okay? All right, so when non-conservative forces do work on a system, mechanical energy is not conserved. So if you go to the back page, Roman numeral number 3 talks about non-conservative forces. Okay? The the next sentence, I realized this morning I didn't have a bullet up here to fill that in. But we talked about this last week. Remember the problem that we did? It showed like a ledge, and we lifted the ball up from here to the top of the ledge. Does that problem sound familiar? Okay. And it ends up with 30 joules of potential energy up on top of that ledge. So we said how much work had to be done. 30 joules, because letter B says the amount of work done is equal to what? What did we say that work does to an object? It causes a...
Decomposition.
That's getting too specific. What does work do on an object in general, Jim? Changing the energy. So, in letter B, underneath Roman numeral number 2, when it says the amount of work done in the object is equal to the change in its mechanical energy. So the amount of work that is done on an object is equal to the change in mechanical energy. It's not
Change to the mechanical energy.
Yep. Mathematically, we represent that with this equation. Okay? WNC equals delta ME. So first, what do you think the W stands for? Work. What do you think the NC stands for? Non-conservative. So the work done by a non-conservative force, right? Remember, we said there are only two kinds of conservative forces. What are they? Gravity and elastic. Everything else is a non-conservative force. Okay? So the amount of work done by a non-conservative force is equal to delta ME. Are you guys familiar with the delta notation from math class or science? Okay. Delta, this triangle, is a Greek letter. It's the Greek letter delta. We use it to represent change. So when we talk about the change in something, whenever delta goes in front of it, we're talking about change in something else. Okay? So in this case, we're using it to represent the change in mechanical energy. Question: if we want to know the change in something, what do we need to know? If we want to know how much something changes, what do we need to know? Maura?
What it started as and what it finished as.
So we can take this equation and we can actually write it a different way. And for some reason, I don't think I wrote it this way. Didn't write it this way. But if we start off with this, MEI, right? Representing what? MEI is mechanical energy initial, right? Then we're going to do some work on it. Might be positive work, might be negative work, but there's work on it. After we do work on it, what are we going to end up with? Okay. That expression, ME initial plus work, right, equals ME final, is the same as this equation here. Okay? And we refer to that as the work energy theorem. The work energy theorem. Okay? Good there? One of the biggest non-conservative forces that we run into is friction. All right? Example. Ready? Here we go. Okay? So, was mechanical energy conserved in that situation? Two reasons, right? What's the first thing I did to the book? Did I do non-conservative work on the book? Yes, because what did my initial force do to that book? It gave it more what? Yes, but from an energy standpoint, it gave it more. What kind? Kinetic, right? So it's flying through the air. Flies through the air, it gets lower, it actually gets a little faster, right? But it has potential and kinetic when I let it go. It still has potential and kinetic when it gets to the ground, but less potential and more kinetic. But then when it hits the ground, that was supposed to slide across the ground and come to a stop, and it ran into that chair. You all just want to see me look at this. All right, here we go. Get another chair. But it comes to a stop, right? Does it have the same kinetic energy when it hits the ground as it does now? Has less kinetic energy, right? Where'd the kinetic energy go? This plays a role. Okay. What did we say about friction previously in this chapter? Does it do work? Yeah, what kind of work? Negative work, right? Oh. So friction does negative work on the system, meaning that mechanical energy is going to decrease. But earlier in this unit, we talked about energy conservation as a whole. When mechanical energy is not conserved, total energy always has to be conserved. So energy doesn't just go away. It changes forms, but the total amount has to remain the same. That total amount including heat energy. What happens to things when friction acts on them? They get what? They get warm. Rub your hands together or rub your hand along your pants. What starts happening to your hands? They get warm, right? That energy is going from kinetic, the motion of your hand, into heat energy. What happened to that book as it slides across the floor? It gets warmer because friction takes that mechanical energy, that kinetic energy, and turns it into heat energy. So friction takes mechanical energy and turns it into non-mechanical energy. That's what non-ME stands for. Okay. And we will use this idea to look at a bunch of different situations tomorrow. Okay. Yes. No, those quizzes are yours to keep. Oh yeah. Oh, sorry. Yeah. Do you guys have your tests from the other day? I gave you those chance to take a look at it. Catherine, why don't we just throw them back in the tray in the back so we can use those for things in. Thanks, Trish. So if you have your tests that I gave you over the weekend, so you can take a look at those over the weekend. Just go ahead and throw them in the back where tests go. Okay.